Okay, so in this video, we're going to look at the difference between conservative and non-conservative forces. Apparently, I misspelled conservative. T-I. Sorry about that. So what happens is certain forces, we call them conservative, okay, because they conserve mechanical energy, hence conservative. I don't want to misspell it here, okay. Which just generally means that then they're going to have some special properties, right? And so remember, mechanical energy, right? We define that as the sum of all the potential and kinetic energy. So it's just simply kinetic plus potential. Okay. Now, what happens is with conservative forces, all of them will have a potential energy associated with it. All right, so that's very important to note that if the force is conservative, we are going to have potential energy. Okay. Now, a conservative force's magnitude and direction only depend on the objects. Sorry, so the magnitude and direction of the conservative force will only depend on the location of the object, not what's happening with the motion. Okay, so one of the big conservative forces is the gravitational force. Right, so it's only dependent on where that object is located, right, to determine the potential energy from that conservative force. Okay, so the work done by a conservative force as an object moves from point A to point B is the same regardless of the path. Okay, and so it doesn't depend on how we get there, right? And so if I have 2 points A and B, right, I can take an infinite amount of paths, right? So here I can do something like this. Sorry, my pen seems to be acting up this morning. Okay, or I can do something like this, right? And so if I apply a force, and that force is conservative, right? Let's just say, okay, so if this force is conservative and going, actually, we would need to direct it along this line, right? And so if this force is conservative, the work done will always be the same, right? No matter how I get there. So if F is conservative, the work done will always be the same. Okay. Now here are some conservative forces. You have gravitational force. I mentioned that one. Gravitational. Right, and that's calculated two ways. F equals mg, or F equals g m1 m2 over d or r squared. Okay. The spring force is a conservative force. Right, F equals negative kx. And then also the electric force is a conservative force. And as we go through, I mean, we've already talked about, right, the spring force. We'll talk about the gravitational force. Sorry, I forgot to finish out the electric force. Okay. But we'll see that they all have potential energies associated with them in some way. Okay. Now, on the other hand, a force that is dissipative, right? So if it is a dissipative force, or what we call a non-conservative force, it is a force that causes the mechanical energy, right, to not be conserved. Okay, so it's going to cause a loss of mechanical energy, right? And that's very important, right? And so a lot of times, just the big, and we're going to talk about some non-conservative forces here in a second, but the big non-conservative force is friction, and the heat comes along with friction. Okay, now on the other side, right, where we talked about how, sorry, I seem to be off today. Right, and so we talked about how conservative forces have potential energies, non-conservative forces have no, excuse me, no potential energy. Okay, and the work done by non-conservative force is path dependent, right? So it matters how it gets there. Okay, so the work will be different depending on how it gets there. So I saw a great picture. All right, so let me do this. So we take this, we have two smiley faces, right? And I have A and then I have B. Okay, and I want to kind of, so here's my second smiley face. So I do it two, not one, right? The student is smiling because they're taking physics. Okay, so if you want to think about it, if I want to erase, I'll take my eraser, and I want to erase from A to B, right? Know what happens if I take a straight line path, and this is not, of course, not going to behave because this eraser does it kind of in bulk. All right, so let's use, okay, and so let's make it bigger. Okay, so let's say I want to cover this up by, going over it with a green pen. So if I take a path from A to B, right, straight line path does not do a lot, right? Now what happens when I take a different path? If I do something like this, right? So you'll see that the smiley face gets covered up more if I do kind of this curved path versus a straight line path. So if the curved path represents the work done, if I take a straight line path from A to B, there's less work done than if I did this curved path, okay? And one thing to know, again, we talk about how the mechanical energy is lost. It's not recoverable in those situations, okay? Now, what are some non-conservative forces? Well, I mentioned one, right? The friction force, right? Friction force generates heat, and heat is energy lost to an environment, okay? The drag force is also a non-conservative force, okay? And then the magnetic force is also a non-conservative force, okay? So if we'll talk about conservation of energy, if at any point in time you do have non-conservative forces, you do have to account for the work done by them by including that in our conservation of energy kind of calculation, okay? So from here on out, right, we're gonna look at potential energies, and then we're gonna do conservation energy, and then finally, we're gonna do power.